Well, hello and welcome everyone. Today's session we're going to tame a wild beast named virtual threads. My name is David, I'm an Oracle ace, which means I like to talk about Java stuff in my free time. And you'll find my Twitter and my website right there. So we have a lot to cover today. And to tame a wild beast, you need to know where it came from. So we're going to talk about some threads from the past. Where did the need for virtual threads come from? And how are we going to solve our concurrency problems prior to Java 21? Then we're going to look into virtual threads. We want to tame this wild beast, so we need to, understand its weaknesses, how it works and everything. And because every story needs a happy end, we need to know how we can live happily together with virtual threads using structured concurrency. And at the end, there is some time for Q&A. So let's start. So this, I think, the most basic example of how you create a thread inside Java. Who has done something like this before? That's pretty much everyone. That's really nice. So what happens here is that we call the thread class. We pass it a runnable task, which is a runnable. And then we call start. And then the thread will magically perform this operation. So when we call this thread constructor, what happens is that our application is making a call to the operating system and asks it to create a resource for us, to create an actual thread that we can use inside our application. So we have to leave our safe application space, go to the operating system and ask it to create, the actual resource, which includes some memory and some CPU time, because nothing is for free. And depending on the operating system you use, it can be almost nothing, but almost up to 1 megabyte for each thread that you create, using the thread constructor. So if you're going to do this a lot of time, you're going to reserve or allocate a lot of memory each time that you create a new thread. So how can we use these the thread class? So prior to Java 5, we just created a thread for every task that we had. So when you have a task, just create a thread that you want to use right then and there. And this is a very easy way of programming, because every time you have a every time you have a task, you just create a thread right on the spot. And this is very easy, but like I said, every time you have to leave your application, ask the operating system to do something for you, which is kind of a waste of resources and time. So that's where Java 5 comes in. With Java 5, we were encouraged to use the executor services instead of the thread class directly. And what the executor service does is that create an easy-to-use pool for us, and we can just submit tasks into that pool. And then the pool will pick up a task when a thread is ready. But there are also some downsides to this. For example, leaking thread local variables. If you have a task that sets a thread local variable, but forgets to unset it because, who's going to remember when you set something? So when this thread is put back inside the pool, it will still have that thread local variable. So the next task running on that same thread will be able to read the thread local variable from a previous task. So that isn't a very nice thing to happen. So you try to avoid that. And of course, blocking methods. Because when you have a task that makes a call to a database, for example, that thread is now blocked outside of the pool. It isn't doing anything useful, it's just waiting. It isn't going to pick up a new task. So while this task is just doing, or this thread is doing nothing, it's just waiting and not doing anything useful. Because remember, those threads are one of the most very expensive resources that we have. And then there is async programming. Async programming tries to solve this, but in my opinion, it's very hard to write. It is very hard to read, especially 2 weeks after you wrote it. And there are chances that you come in contact with what is called the callback hell, and then you really want to start doing something else. And of course, it is hard to debug because the Java, the application is really built around stack frames, and when you start doing async programming, that really goes out of the door. So that's why it's not really a preferred way. But the great thing about it, you have all these downsides, but the upside is it makes very good use of the resources. And that's where virtual threads come in. Virtual threads are an alternative implementation of the thread class. So the thread class that we are already familiar with, that isn't going anywhere. We just get a new type that we can use. So to tell them apart, the threads that we already have from Java 21 or Java 2018 and prior, those threads are still there, but we now call them platform threads because they are managed and scheduled by the platform. But we call these virtual threads because they're managed and scheduled by the application itself instead of the operating system. So the great thing about these virtual threads is, like it says, is that the operating system doesn't know anything about them. When you create a virtual thread just inside your application, they are just a concept that lives inside the JVM. And the great thing about this is that now the stack frames of this virtual thread now live inside the heap, which means that we can resize it, or the application can resize it, the memory usage, when needed. Because with a platform thread, we have to allocate the full memory that we may or may not use in advance. So with the platform thread, I have to allocate 1 megabyte if I'm going to use it or not. But with virtual threads, I can just start out with a very small amount of memory, just maybe a few bytes, and if it needs more, I will just allocate more for it on the heap. So the heap is now, or the stack is now resizable. And that's what makes these threads very cheap to create, because you don't need a lot of memory to create a lot of them. So, and how much memory do you need? So I created 2 applications, one that uses virtual threads and the other one uses the platform threads. And I just started to see when does it start making sense to use virtual threads over platform threads. So if your application doesn't use more than 1,000 threads, then maybe rewriting the whole thing isn't really worth it, because you're only doing it for a small change in memory usage. But if you start looking at the right side of the graph, it's like 1,000, 10,000, or even 100,000, you really can see that the memory usage starts taking off. And with 100,000 threads, the platform threads just gave out because of an out-of-memory exception. So you could look at it as if the application was very good with its resources, but you don't have an application at all. So the virtual threads are the way to go if you really want to use a lot of threads. So let's see how we can create one of those threads. So, like I said, a virtual thread is just a new implementation of the thread class. So I'm going to create a new virtual thread using the thread class, which has now a new method called startVirtualThread. And what this method does is that I can pass it a runnable. It will immediately start running inside the virtual thread. So I don't have to go start, so let me run this. The computer is thinking. Well, let me zoom in. So, and as you can see, you have just been greeted by a virtual thread. So in just 2 easy lines of code, well, one if you don't want to do the join, you can just create a virtual thread on the spot. And this is how you are supposed to use them. Just create them right then and there when you need them. So one method is nice, but we also get a new builder method by using off virtual or off platform. With platform, I will create just the threads that we already know, the platform threads. But if I want to create a virtual thread, I just have to use the off virtual. And then I can set things like, for example, the name. So I'm going to call this one VT name. And I can give it a unstarted task. I can also give it a started task, and it will immediately run. But just for the demo effect, I will just go start, and then a join to print something to the console. And if I run it again, it prints hello everyone again, which is really nice. So with Java 5, we are encouraged to use the executor service. So with Java 21, it also got a little update. And is that now the executor services now implement the auto-closable interface, which means that I can use it together with the try statement resource, the try statement. So I can use executor service. I'm going to call this a VTE instead of the new virtual thread per task executor. So what this executor does is that it will create a new virtual thread for every task that I submit to it. So for example, I'm going to create the for loop, and let's create 100,000 threads because that's fun. And just let them sleep for 1 second. In production, you would never try and create threads just to let them sleep for a second, but it's perfect for a demo. So it's going to create 100,000 threads. All of them are going to sleep for 1 second, wake up again, and then the program is over. So the great thing about this try with resource statement is that I don't have to call join or anything. To exit this try, all the threads that I created within it need to be finished, either by exception or successfully. Only then can I exit this try statement. So what happened is that I just created 100,000 threads, and they all slept for 1 second. So how does this work? How do they get time on the machine? Because I'm only running this on the laptop, and I don't have 100,000 cores. So what I just did looks a bit like this. I created a bunch of virtual threads that run on, for example, 4 cores. So let's say that this machine has a 4-core system. So how do these virtual threads map to a core? So these virtual threads, they don't run directly on the machine, but they run on what is called a carrier thread. And a carrier thread is nothing more than just a platform thread designed to execute the tasks of a virtual thread. So a virtual thread doesn't run directly, it runs to a carrier thread. So if I zoom out a little bit, then you can see that these virtual threads that I created, all 100,000 of them, live inside a queue, and they get assigned a virtual thread, or sorry, a carrier thread, and this carrier thread starts running this task. And of course, the carrier thread is just a platform thread that is managed to schedule by the operating system, so all the way down. So these carrier threads will run the work of the virtual threads, but how does it know when to switch, or how do you manage the carrier threads? Yeah. So like I said, you get, I have a 4-core system. So by default, I get 4 carrier threads. But of course, you can change this using the manage carrier threads, using the virtual thread scheduler parallelism parameter. By default, you will get as many as you have cores inside your system. So a 4-core system, you will get 4 carrier threads. But if I change it to 5, then I will have 5 carrier threads by default. So how does a carrier thread know when to switch from one virtual thread to another? And that is done through mounting and unmounting. When a virtual thread is blocked, it will be unmounted from the carrier thread. So the memory, so the stack frames of this virtual thread are copied from this carrier thread back into the heap. So it is really physically taken off the carrier thread. And a new virtual thread will take its place. So from the queue, a new virtual thread is taken, and it will be mounted on the carrier thread. So the stack frames are copied from the heap into the carrier thread. So if you zoom out a little bit, this is the complete cycle, is that they all go back into the queue, and a new one is taken from the queue to run on the carrier thread. So the great thing about this is that while the virtual thread is waiting, it is in a blocked state, it is waiting inside of the queue. It is not blocking the carrier thread, which is a very expensive resource, but it's now just waiting in the background. And that is what makes these virtual threads really great, is that they are very good at waiting, just sleeping, just doing nothing. Because they don't run any faster, they just, well, like to sleep. And then just one side note is that the virtual threads, as you can see, they don't always run on the same carrier thread. So it's not guaranteed that your virtual thread will run on the same carrier thread as it did before. So let's switch it up a little bit, because I created a little demo that I have to find the right IntelliJ window. So what I want to show you is something that I found out, is that when virtual threads work and when they don't work, so that we all know that there aren't a silver bullet. So I created a little application. It's just a simple Spring web app, which has two mappings for random pages. So I can have a random page, it just generates a page with 100 URLs on it without a delay, so it will return immediately. And I have one URL which will also generate a lot of random URLs on a page, but it will sleep for us just a tiny amount, somewhere between 10 and 200 milliseconds. So it's quite random, so I don't know what it's going to be, but it is going to sleep, and then it will return also some pages. Because, like I said, virtual threads are very good at waiting, and everybody, it is pretty much assumed that virtual threads work very well with I/O-related tasks. So let's see what it does when you try and put it to the max. So I just showed you just the web server. So now I'm going to crawl the web server, the Spring web server that I just showed you. So as a seed, I have this local host, this URL with the delay. And I'm going to use the new virtual thread executor. And I'm going to submit 400. I want it to crawl 400 pages, only then it's done. So let's see how many pages it can do in a second. So let me zoom in a bit. So with virtual threads, I'm able to do 574 or 47 pages a second. And let's see what happens if we try to do this with platform threads. So the threads that we had before. Just to show you, it has the same amount of it uses the same amount of threads as the virtual threads do. So with virtual threads, I will get, I think on the machine, 8 carrier threads. So just to make it equal, I will also create 8 platform threads. So let's see how many pages I can do with the platform threads. It takes a while because it's slower. And it shows me 124, which tells me that the platform threads are a whole lot slower than the virtual threads, which is quite as expected, because I have to go out of my machine, I have to wait a bit for the Spring application to create a result. So let's try and do something else. Let's switch it up, because I have also the other endpoint without a delay. So it should be much faster, right? So here I am doing it with the virtual threads. It gets 836 pages a second. Let's just run it again just to see if maybe it can be a bit quicker. 746 and 840. Okay, so 840, I think that's around the max that we can get. So let's try and do the same thing with the platform threads. And with platform threads, I'm able to get 1,238 pages a second, which means that even though it is an I/O-related task, the virtual threads are underperforming in comparison to the platform threads. So even though the virtual threads are supposed to be quicker because of the whole non-blocking and or the mounting and unmounting and the whole blocking stuff, if the blocking doesn't take enough time, let me go back to the presentation. So with the virtual threads, I'm forced every time I make a web request, I have to unmount it and mount something else. Well, the platform threads don't have this issue. They can just wait on the spot. But with the GET request that I'm doing every time to this web server, I'm forcing the virtual thread to be blocked, to be unmounted, and to be mounted again. So every time this does take some time. It's not for free. It's just to show you that virtual threads are not a silver bullet. So the virtual threads, they don't always get unmounted. And that's when we say that a virtual thread is pinned. The virtual thread is then pinned to its carrier thread. It can't be taken off. And that's because not every method is ready yet. For example, the synchronize block, the object.wait, or call to native code using something like GNI, causes the virtual thread to block and to be pinned. It says in the title yet because they are working on an issue or to resolve it, but there is an early access build of Java 23, which should resolve this, but they are looking for feedback if the performance is right. So, but if you are using 21, then this is still a blocking or pinning operation. And when a virtual thread is pinned, so the carrier thread then is also blocked, then the application can decide to spawn more carrier threads and to create a max pool size. So for this example, you have the max pool size of 10. Then the application can create that many extra carrier threads. So if I have, by default, I have maybe 4, and then it can go up to 10. So then you can get more carrier threads to just prevent the degradation of performance. And to see if a virtual thread gets pinned, you have these two options, this run option or this system property, that you can set, and it will show you a description of when a virtual thread is being pinned. It will show you a little stack trace. In the short description, it will show you just a few lines, but with the full, you will get the full description that is available. I must say that in my experience, the full description is the most helpful, especially if you are working with lots of third-party libraries. Because otherwise you don't know really where to look. So the pitfalls of virtual threads is that you don't want to use them for long, well, not blocking calculations, because like I said, these virtual threads, they are very good at waiting, just doing nothing. So if you're going to put them to the test and make them work very hard, then it's just recommended to use the platform threads. Don't use virtual threads just because like I showed you with the web server scraper, you would say that it is a very good use case, but still, only then it still underperforms to the platform threads in certain situations. So testing really is key in comparing if it really has a good effect on your application. And of course, old libraries may still use the unsupported methods and still cause a bit of pinning. So that's something to look out for. And like I said, these virtual threads, they aren't any faster because, well, they still run on a carrier thread, which is still a platform thread. So they are just a nice little abstraction to create a bit more threads than you can before. And then just a few design thingies is that you want to create virtual threads right when you need to. You don't want to pull these virtual threads. That's really an anti-pattern. You should just create a virtual thread for every task that you have. There are some code bases where people use a pool of threads to limit access to a resource. But it would be better to just replace that with a lock instead. So, virtual threads are great, but I like structured concurrency way better because it makes dealing with virtual threads a whole lot easier. And because it's quite a new concept, and it also took me a little bit, well, a lot of time to, well, get to know how it really works, I want to start, well, really simple with just this little bit of structured code. And I think everybody, should be able to, well, know what this application does. I have this method A, I run B, then method C, and then I will create some result that I can return to the caller. And the great thing about this structured code is that it tells me exactly what is happening when. So inside the lifetime of method A, I will first call B, I will then call method C, then I have a result that I can return to the caller of method A. And when something happens, I know exactly that I can stop right then and there in a moment. So when method A is running and method B throws an exception, I'm not going to try and call method C because it doesn't make any sense. And I'm not going to try and create a result because I am missing B. And the same goes for if C throws an exception. I'm also not going to try and create a result. I ran B, but yeah, that's just a waste of time, but I can't really do anything about it. So I'm not creating a result. So let's take the same example, but now add threads to this. And then I have, again, the lifetime of A, but B and C run in parallel. So I have C and B running at the same time. And when both of them are ready, I have a result that I can return to the caller. And now the same thing happens. Method B throws an exception. But what happens is that method C just happily continues running. It isn't really bothered that method B throws an exception. Method A also doesn't really care. But when I'm trying to create a result by foo.get, Then I notice, wait, my thread threw an exception, I can't create this result. And then I have to get out of my way and try to stop method C from running. I have to kill that thread in one way or another. So there's really this implicit relationship between these three threads. I have a thread inside C, B, and of course the parent that is running inside that's running A. And of course method C can also throw an exception, but it's a little bit worse. Because now method B is running, I have to wait for it to finish, which can take X amount of time. So the foo.get finally returns, and then I do the bar.get, and I find out, wait, I have waited all this time for B to finish, but I could have stopped way earlier because, well, I can't create the result that I want. So I could have stopped way earlier. And of course, the parent thread could also just, well, stop running. And then I have two threads running inside my system that I need to stop, and I don't know how, I don't really have a reference to them. So, good luck. Which isn't really nice. Not a great situation to be in. So, with restricted concurrency, this tries to resolve it and make this whole relationship between those threads a bit more explicit, so that the next developer knows what you meant when you created the method. So let's see how we can do this in Java. Just zoom in a bit. So the way structured concurrency is implemented in Java is with the structured task scope. The structured task scope, we get two flavors with 21, which is the shutdown on success and the shutdown on failure. And what this is that it are two policies that state when the virtual threads that you created have to stop. So with the shutdown on success, the policy states that I want either my virtual threads to stop when the first one has finished. So I only want the quickest result. So I'm going to create in two threads using the scope.fork. And the scope is of the structured task scope .shutdown type, and it will return a string. So using the scope, I can fork new virtual threads. They will immediately start running. And they are of the type of virtual, and they will be a virtual thread. So I will create two virtual threads using the fork method. And then I will do a scope.join. And with the scope.join, I'm saying I will wait here until one of the threads has finished. And then I want to continue. So when I run this example, we are going to see which one finished first. And as you can see, the first thread returns the quickest. So if the second thread has finished, the result will be ignored. If it was still running, it will be cancelled. And using the scope reference, scope instance, I can get the result of the thread that finished first. And of course, this also happens inside this try statement. Scrolling is hard on this resolution. So this is the first structured task scope. So the second one is the shutdown on failure. And the shutdown on failure, so let me make this a bit bigger. And the shutdown on failure policy states that I want to shut down all my virtual threads if one of them throws an exception. So either they all finish successfully, or if one throws an exception, I will just stop. So again, I will create a try with resource statement, create a new scope, this time of the type of shutdown on failure, and I will fork two new virtual threads. And I use the subtask. I believe you can also use the supplier, but the subtask shows you a bit more information about the virtual threads and its status, so I think it's a little bit nicer. Shows you more options. So, and then I have a subtask A and B. And I'm again doing the scope.join, but because we saw that in the last example, I'm going to make it a bit more exciting by using a deadline. So I give the threads, both virtual threads, 10 seconds to finish. And if they don't finish in time, I will just throw an exception. And at the end, I have to throw a failed. And the throw a failed will rethrow the exception that has happened inside one of these threads if one has happened. And then at the end, I will get the results from both threads. So when we run this, you can see that it printed result 1 and 2. So both threads were successful, and they finished within the allocated time of 10 seconds, which is really great. So, but there are some moments where you really want to go, and create one of your own. So you can also create your own structured task scope. So let me show you what I want to do, is that I want to create a criteria scope, because I'm looking for a product. I'm looking for a product that is worth less than 100. So I have 3 search methods, really. One that gets a product of 50, one of 300, and one of 200. They all have a little bit of a delay, so I don't know. I don't know is a really big word, but as you can see, the product of 50 will sleep for 0 seconds, 300 will sleep for 10 seconds, and product of 200 will also return immediately. So let's give this one a bit more time. So product 200 will also return. So what I will do is that I have here a structured task scope, or the criteria scope that I created, which extends the structured task scope, and it will return of product. And what you want to do is override the handle on complete method. Every thread, when it finishes, will call a handle on complete method. And then using the subtask parameter, I can check the state, see if it was successful, because I'm only interested in threads that really find the result and not the failing ones. And if it was successful, I want to check if the price is less than 100. If I found my product, I'm going to save it for later and shut down. So the threads that are still running will be shut down, and I can, the join can continue, and a simple get method. So when I run this example, you can see that product 50 was a success, 300 as well, and 200 too. But the product that is found was 50, and with 50 the shutdown method was called. And then I waited for the same. Let's try it again to show you. That will also stop a virtual thread. So what I now just did was I made product 300 return a little bit slower. So as you can see, product 50 was found, it was successful, 200 was successful as well, but 300 is unavailable, this thread was cancelled. So it didn't finish in time. So the pitfalls of not using structured concurrency really is that you have to do the joining, exceptions, timeouts all yourself. So the managing of those lifetimes is something you get out of the box with structured concurrency. And that makes it really nice if you have lots of virtual threads that all need to be managed. So all you need to get started with virtual threads are really just these 2 methods. The start virtual threads, which takes the runnable as a parameter, or the new virtual thread task executor to start working with virtual threads. So now it's time for questions. Yes? Sorry? No, there's nothing like that. You can use these scoped values if you want to return something back, or... Sorry? What? Oh, in Go? I'm not that... Yeah.
So in Go, you have to add functions to give back the context to the carrier thread, because if you don't do that, if you put a loop that the coroutine, the same thing of a virtual thread, it never gives back the context, so it runs and it is never scheduled, that will never unmounted, right? If you talk about Java language. So in Java, do you need to do this kind of thing, or the JVM already does this automatically?
This product you mean, that from the last demo you mean?
Sorry?
I'm not really understanding the question.
Sorry. No, it probably does not happen in Java, because Go only gives the thread back to the carrier thread when it's sure that you can context switch. So it only does this during a function call. While the Java probably it does not. You do not need to have this, right?
No, you don't have to.
Okay. Because in Go, if you have a virtual thread with a loop, it will never give in no function call. It will run as a single threaded thing and not give the context back to the other threads, the other virtual threads.
Okay. Yeah, thanks. Yeah, I'm not that familiar with Go, so it's really hard to answer the question.
Yeah, sorry. I wanted to know because I use it to this. I have to put a lot of function calls. We can't have without function calls. But it's good to know that Java does not do this. Yep. Thank you.
Yes?
I don't know if you know Quarkus, but we have SmallRye framework that use uni and multi to create a synchronous task and so on. Reactive Quarkus is based on that. How we can compare this with virtual threads?
Sorry, no. Yeah, it's really hard to understand. Sorry.
You don't know SmallRye uni or multi framework?
No, I'm not familiar with the framework, so that's.
Forget. Thank you.
I mentioned that virtual threads can be scheduled to different carrier threads.
Yeah.
Does it cause any problems, considering that stack is in heap, not in
no, yeah, everything that is getting copied into the carrier thread will also be taken out of it. It will be just taken back into the heap, and then it will just.
No, I mean when you work with virtual thread, it's just a fun fact. You don't need to take it into account that it can be scheduled to different.
No. It's all happened behind the scenes, all taken care of.
Okay.
So the whole blocking.
I mean, there are no some pitfalls related to this.
Sorry?
There are no some hidden problems related to this fact. That virtual thread can be scheduled to different carrier threads.
No, just the. No, the only thing that happens if you have the thread local variables, because you're going to create lots of virtual threads, that also takes up a lot of memory. So that's when you want to use these scoped values, but I don't know if there are any issues with just frameworks and the whole scheduling on different carrier threads. It's all abstracted away for the developer.
If you use thread local, it will be local to virtual thread or to carrier thread.
Sorry?
If you use thread local, it will be local to virtual thread or to a carrier thread.
Sorry.
Thread local variable. It will be in virtual thread stack or in the carrier thread
the
stack.
thread local variable will still be in the virtual thread.
So it's also not a problem.
No, then you really want to use these scoped values.
Okay. Thank you.
So in case of you need to extract some thread dump for the memory, of course your application doesn't have problem, but if so, will be the virtual thread present on the thread dump from JVM?
I don't know, never tried.
It's a good question, man.
Yeah. It's a fair
All right.
Hello. First of all, thank you for the presentation. If I understood this correctly, carrier thread can be seen as a platform thread. So
Yeah.
it includes all the costs it is involved in as a platform thread. Is there some sort of pooling for these threads as well to optimize? Is it done under the hood? Should we also take that concern into account?
Yeah, those carrier threads, they run in the fork join pool. So this fork join pool takes care of the whole scheduling and running part. So yeah, there were some plans in the beginning what I read from the mailing list is that they want to let developers create their own schedulers, but that's still talk for the future, and I hope they will somehow implement it, but
Okay, but
not yet.
as a starting point, we don't need immediately to be worried about that. It's already kind of taking advantage of some pooling mechanism behind it.
Yeah, it's already taken care of. So
function.
you only have to just create the threads.
Thank you very much once again for the presentation.
Hi. In your last example of the structured concurrency, what actually happens to the threads that do not finish? Do they get an interrupt or do they keep running? Because you were swallowing in your example the
they will
interrupt
get
exception.
they will be interrupted if it supports the interruption. Depends. The sleep method does, but if you are doing, for example, a very long running calculation, just
So it might happen that the virtual thread keeps running.
Yeah,
indefinitely.
there is the
And
case
so
that it just keeps running, but it gets the signal. If it gets ignored, it's
yeah,
ignored. If it's
I was just
supported.
wondering if it gets forcibly unmounted and just dies. Or, yeah.
In a sleeping situation, yes, but yeah, it's,
Yeah. Okay. Thank you.
Hi, so thank you for the presentation. One of the things you said in the beginning was, I think we all agree, is that multi-threading application, debugging multi-threaded application, it's hard. With virtual threads, is there any advantage to debugging or the process stays the same?
The benefit is that it works exactly the same as that you're used to it with the platform threads.
Okay, so it's basically
So
the
that's
same.
the big benefit. That with the, for example, the async programming, it gets a little bit more difficult. But with the virtual threads, you get to write your code just like this. So
Okay.
that's the benefit, and then it makes debugging just a bit easier.
Okay, thank you.
Well, if there are no questions left, then thank you for attending.